How's it going, everyone? Welcome to another video on matrices. Today we're going to have a look at the application of matrices to solve simultaneous equations. To start off with, we're looking at solving equations with one unknown. So for the example I've got here, we've got 2x plus 1 equals 5. So it's got one unknown, meaning we only need one equation to be able to solve for that unknown. So just from previous years, if we were to solve this equation, we'd have 2x equals 4 by taking away 1, and then x equals 2 by dividing by 2. So that's solving just a linear equation. It's got one unknown, only one equation is needed to find that unknown. Posing the situation where we have two unknowns, so we've got x and y now. So to be able to solve this equation, we need, well, basically we need two equations. Because we've got two unknowns, we need two equations. So we've got 2x plus 3y equals 13 and 5x plus 2y equals 16. So because we've got two equations, we've got two unknowns, we'll be able to solve that equation. And what we're going to look at in this video is how do we use matrices to solve these simultaneous equations. So from previous years, you may recall other methods for solving simultaneous equations. So we're using matrices as another tool, and it's another useful method for solving them. To start off with, we'll consider a pair of simultaneous equations in the form as followed. So we've got ax plus by equals e, and we've got cx plus dy equals f. So this is what two equations for two unknowns will generally look like. So a, b, c, and d, they're going to be numbers, coefficients. X and y are the two unknowns that we're trying to find. E and f, they're going to be numbers as well. All right, so it's very similar to this example over here. So the coefficients in front of the x and y and the 13 and 16. So the equations can be expressed as a matrix equation in the form ax equals b. And we say matrix A will be the coefficients in the first on the left-hand side. So that'll be A, B, C, and D. And this is called the coefficient matrix. So A, B, C, and D are the coefficients next to x's and y's. After that, we've got the unknowns, which are x and y. So start off with, find your coefficient matrix. Your unknowns are going to be just the x and y. And using this general equation over here, we have b, which is going to be e and f. All right, so that's the equation expressed as a matrix equation in the form ax equals b will look like this. So we've got matrix A, here's our unknowns, and here's matrix B. So as we've seen in previous chapters, an equation in the form ax equals b can be solved using our inverse operations. So we start off with ax equals b, and we're trying to find x. That's our unknown matrix. So from past chapters, we would find our inverse of A, the matrix inverse of A. We'd multiply it on the right because A is on the we'll multiply it on the left because a is on the left of x. And what we do to one side, we've got to do exactly the same on the other. So again, multiplying on the left. Now a and inverse of a, that's basically our identity. It's like multiplying by 1. So basically they cancel out, which is what we want to do. So we're left with our unknown. And our unknown is equal to the inverse of a times b. Okay, generally pretty quick and easy to do it this way. Now you could start off with by putting your matrix A in and matrix B and solving it like that. This is another way, and we've had a look at that in previous chapters. Simultaneous equations are not limited to 2 equations and 2 unknowns. And basically the same method applies as we get bigger. So I've just shown where we're trying to find 2 unknowns. If we were looking for 3 unknowns, for example, we would need 3 equations. So 2 unknowns need 2 equations, 3 unknowns would need 3 equations, and so on. So to solve these unknowns, 1 equation is needed for each unknown. We're going to consider a quick example. So the ancient Chinese problem dates back to one of the oldest Chinese mathematics books, the 9 chapters of the mathematical art. Bit of history. Basically what it says is there's 3 types of corn, of which 3 bundles of the first, 2 of the second, and 1 of the third make 39 measures. The other situation is 2 of the first, 3 of the second, and 1 of the third make 34. 1 of the first, 2 of the second, and 3 of the third make 26. And the question asks how many measures of corn are contained in 1 bundle of each type. So this situation is, one method of solving this is using matrices. So just going to break it up a little bit, just looking at the second paragraph here. So there are 3 types of corn. So we've got 3 unknowns. Basically x, y, and z. You can use any other coefficients or unknown that you want to use. So you could use a, b, and c. I'm just going to use x, y, and z. So we've got x, y, and z. And all up, it makes 39. So what I want to do, I'm spacing it out a little bit. I've got 3 bundles of the first type. So I've got 3 types of the first, 2 bundles of the second, and 1 bundle of the third. And all up, when I add them together, I get 39. So there's my first equation. Now I've got 3 unknowns, so I need 3 equations, and it's just so happened that we've got 3 bits of information. So we'll look at the second equation. We've got 2 of the first, we've got 3 of the second, and 1 of the third. And all up, when we add them together, we get 34. And the last one, we've got 1 of the first, we've got 2 of the second, and we've got 3 of the third. And all up we've got 26. So now I've got 3 equations, 3 unknowns. I can use this information now and translate it into matrices. So just like before, my first matrix is going to be the coefficient matrix. Basically, it's all the numbers next to our unknowns. So we've got 3, 2, and 1 along the top, 2, 3, and 1 and then 1, 2, and 3. The second matrix is going to be our unknown, so x, y, and z, and they're all vertically. Once I've done that, I have 39, 34, and 26. So again, like before, I've just translated all this into matrix equations where we've got AX equals B. So matrix A would be the coefficient matrix over here. Matrix X is our unknown matrix. And then matrix B is on the right hand side. Now I'm not going to solve this right now. You can do it if you want to have a go. Basically, as a general rule of thumb, to find the inverses of matrices, if its order is 3 by 3 or 4 by 4, basically anything more than 2, we use our Casio. So because I've got a 3 by 3, it would be easier and more efficient to use Cas. If it was a 2 by 2, then I would use method by just by hand. But because it's 3 by 3, I'm not going to do it by hand. It'll take too long in this video. Just as a note, while we're on inverse matrices, just remember that if we find the determinant of a matrix is 0, the inverse will not exist. Basically, it means we've got two situations. Either there will not be a unique solution for the system of simultaneous equations. It means that we've either got no solutions or there are infinite solutions. Uh, Dependent systems of equations. So this is elaborating on that last little note. So if the graphs of two or more solutions coincide, meaning that they are the same line, then there is no unique solution for the equations. Therefore, we say the equations are dependent. If we try to solve dependent equations using matrix methods, then we would find that there would be no solution as the determinant of the coefficient matrix is 0. Okay, just going on before, we find, all right, solving AX equals B, if we find that this inverse of our coefficient matrix, so if the determinant of A equals 0, then we don't have a solution for our inverse matrix. And inconsistent systems of equations, if the graphs of two or more equations do not meet, then that is, if the lines are parallel, then there is no solution no solution to the equations, and we say that the equations are inconsistent. Again, meaning that we get a determinant of the coefficient is 0. There's no solution for the inverse. So summarizing all that, what it's meaning is, because we're talking about equations of straight lines, basically. Okay, here's our first line. For the dependent systems of equations, means that they are the same line. So basically, if we find that the first equation equals this when we graph it, if we were to graph it, and then we look at the second equation, it would actually turn out that that would be exactly the same as that line, and all the points are going to lie on top of the first, meaning we have infinite solutions. So every single point along here is exactly the same as the equation before. The other situation is the inconsistent system of equations, meaning we have basically again the same line, but it's parallel to the first. So it never actually touches the first, and that's what we're trying to find. Basically, we're finding the intercept of the two lines when we're finding solutions for systems of equations or using simultaneous equations. We're finding where the intercept of the two lines, where do they both meet? But if we have a parallel line, they're never going to meet, meaning we don't have a solution, which is why we don't have a solution for the determinant, the inverse, sorry. Just finishing up, matrices are a very efficient tool for solving problems, especially when there are two or more unknowns. If we have one unknown, it's probably just easier to use algebraic methods. Um, so matrices are used in many areas, such as engineering, computer graphics, and economics, to name a few. Um, we are going to use matrices in other methods of the further course. We could use it in the break-even analysis, looking at financial maths. So the other thing is looking at finding the first term and the common difference in arithmetic sequences, and it can also be applied to linear programming. Last little bit, so when answering problems, regardless of what situation it is, a few steps might be handy to follow. So first one, read the problem several times to ensure you fully understand it. That's essential with any kind of math problem. Second thing is to identify the unknowns and assign suitable pronumerals. So I used X, Y, and Z. You could use A, B, and C. Could be anything else you could think of. Part 3, or step 3, identify statements that define the equations and write the equations using the chosen pronumerals. So my little example before using from the Chinese over here, I broke it up into little paragraphs here. So here's 3 bits of information. That's talking about my first equation. The second part was my second, and then the third. Okay, so it's handy to break it up into steps like I did there. Uh, Part 4 is use the matrix methods to solve these. So the hardest part really is going to be 2 and 3 for the most part. Okay, identifying the unknowns and finding the equations from the information given. Part 4 is using our matrix or applying our matrix methods to solve the equations. And again, as a good rule of thumb, for matrices of order 3 by 3 or higher, just use CAS. If it's 2 by 2, go for it. Use it by hand, but 3 by 3, it gets complicated. It's doable, but just use a CAS. So I'm going to end it there. In the next video, I'll go through a few more examples. Thanks for watching.